Okay.
Hello?
Can you hear me?
Yes.
Yeah. Okay, good. How's your classes going? You also teach, right? I assume. Can you hear me, Ken?
Yes. Yes, I can hear you much better now. Thank you.
Okay. So let's see. We almost did not have a week of classes. So what is this? I did post homework 4, or is it homework 3 that's going on? Do you remember, Ken?
It's homework 4. Homework 3 is due today, I believe. When you change the due date, it's due today.
I did. Did I change it, by the way? Or I haven't changed it, maybe.
Yeah. The homework 3 is due today with the new change due date, and homework 4 is due next week.
Okay. So let me make sure I did it. Give me a second. Oh, I cannot check it, right? Because it's on D2L that I change. Oh, yeah, but okay. Okay, yeah. So homework 4. Yeah, so let me announce that here.
Yeah, you have it as the
Homework 3, I
23rd.
noticed you had submitted quite early, right?
Yeah, I submitted homework 3 a week ago, I believe. And homework 4 is due the 23rd on D2L.
That's correct. Yeah, that was what I was going to announce. Okay. And hopefully we will have enough information for that today. That's what I postponed. In principle, it is doable because I introduced the basic idea of functional derivative, but still, okay. Okay. So we have homework 3, that's over, homework 4. It's due on Tuesday. And midterm 1 is on March 2nd, so 1 week for Tuesday. So we are surely behind, but we'll see what can be done. Hopefully somewhere down, I'll cut down on examples and such things. Any general things, any comments or anything? So that should be, as far as due dates go, that should be clarity there. We were doing functional derivative, and we were specifically working on examples where you see functional derivatives. And one of the examples we discussed is geodesics, right? If you want to find the shortest path on a surface, in this case, but it doesn't have to be a surface. We can talk about a volume. For example, if I'm in this classroom, and if you have to go from one corner of the room to the opposite corner, in the sense diagonally opposite corner of it, if you think of it as a cuboid, the whole room can be thought of as a cuboid. And if you are a fly, you would take the shortest path, right? You will just fly from one end to the other end. But then you can always say, what if you're not a fly, you have to go on the surface of a room, and there are various ways of working this out. This gets more interesting if it's a curved surface. For example, what is the shortest path on the surface of a sphere? And we sort of gave a hint on how we can proceed on that. And that's one of the examples we will do probably on next Tuesday. And that's all based on making the shortest distance between 2 points. We can also talk about shortest time between 2 points, and that is what happens in optics remarkably. Whenever light travels from one point to the other point, even if it was a complicated system like a galaxy, it turns out that if you know the refractive index, basically refractive index is nothing but the velocity of the light at each point in space. Right? And if you know the refractive index, you can pretty much tell what's the path of light, because at each point it obeys Snell's law. Snell's law is a statement of minimization of the path of light in such a way that the time taken from one point to the other is minimum. And especially time, remember, is one way. It only grows in time. You cannot go back in time. So in that sense, that is this philosophically interesting question that system sort of knows what it's going to do to begin with, even though it hasn't reached there physically to a certain extent. But leaving that aside, if we simply think of it as a system and with a given refractive index, so let's do an example on Fermat's theorem. I will do one example, and the homework will cover another example of the same kind. So I think it's called, is it called Fermat? I think it's Fermat's principle, maybe. Fermat's theorem. There is another theorem which is the number theory, right? I think it's Fermat's principle. Am I right? Ken, please try to say something.
Yeah, it's Fermat's principle.
Okay, that's principle. Okay. So let's consider a specific scenario where the refractive index in a medium is given. So this is how do you say, a layered systems, but the refractive index is continuously changing with time. So let's say this is this could be what's the dependence I would like to have. Yeah, let's say n of x. Right? So this is x, and that's my y. Straight. And refractive index changes as you go in this direction. But it is independent of y. If you keep your x fixed and you change your y, it doesn't change at all. And somewhere around here, let's say x equal to a, there's a simple feature that for anywhere less than that point, it is basically vacuum. This side is vacuum. And by vacuum, we mean that our refractive index is 1. So what we're saying is that refractive index is equal to 1 for x less than a. And from once you cross this point where x is equal to a, and then it starts increasing. Like so, right at x equal to a, it is 1, and it starts to increase such that it is x over a. Right? If x is equal to a, that's equal to 1, and then grows linearly. So this is the case. So that's our refractive index. If we were to plot this as a function of x, so this shouldn't be confused. So this is the actual physical system, and here I'm plotting n as a function of x with respect to x. So you should probably change this a little bit. So it's actually 1 everywhere, and right at a, it starts growing linearly. And it keeps increasing for ever. Right, yeah. Very idealized system. As you go deeper and deeper into the positive x plane, refractive index keeps increasing, and in fact, light will kind of come to a stop, right? When the refractive index is infinity, then velocity is 0, right? Remember your refractive index definition. Refractive index is c over v. So if this is equal to 1, that means this is a vacuum, and if this is infinity, that means it comes to a stop. So light coming to a stop is sort of an interesting phenomenon. And this has been, by the way, experimentally achieved where you can actually reduce velocity significantly, and there has been significant amount of claims saying that you can stop light to a certain extent, but that's all on an average basis, so all that should be interpreted in the right way. Okay, so that's our system. Hopefully this is clear enough. In your homework, this is entirely different in the sense it's exactly opposite. Like it is 1 on the right side, and on the left side, between x equal to 0 and x equal to a, it changes as 1 over x, so it actually grows right until the origin. So it is it's sort of an inverse problem, but it is since infinity is onto the right here, when you flip it between 0 and 1, this whole region gets squeezed in between 0 and a, if you want. So in a sense, it is interesting, and the path that the light takes in such a region gets interesting because it's a finite region. In this case, it's an infinite region. So that's your homework. So it runs parallelly in principle. Okay, so in such a system, you actually let light go from one point to the other point, right? So you can pick any 2 points in this system. It can be on the left or to the right. Pick any 2 points. So let's have arbitrary points somewhere here, and we ask the question, how does the light go from there x2 there. So let's say this is x1 or y1 and x2 or y2. Let's take a small element there. We know that time taken to travel a small element would be ds. This is not dx, this is not dy, divided by the refractive index, right? Divided by velocity if you want. So divided by the velocity at that particular point. So wherever this dt is, we have to calculate that. Change that here. But v is nothing but refractive index. So this is the same as n of x, or n of x times ds. Right. And there is a c also. So instead of writing the c or dividing out by c, so I'll multiply the c down here. So that we are talking about c times dt. That way the dimensionally everything is distance. It's not necessary, but it's just a convenience. We don't have to have c on the right hand side. Okay, so that's our a small element. So if I need the total time, in principle, I just do the integral, right? So c times the total time along a path. I don't know which path I'm taking, right? I only know the end points, and the total time it takes to go along a path is equal to the integral c dt along a path. So let me specify this x1 y1 to x2 y2, and I'd also specify the path. How do I specify the path? The best is to connect the 2 points, right, using a function y of x. So the path is actually, so the path here is y as a function of x. I have to put that information onto the left. So this is now for any given path, I have a time. So that's a functional of that. Okay. Any questions on until here?
You made the path y of x because of the refracting index being an of a function of x, right?
Yes, that's correct. You can also, maybe your question is that I can also say that this is also perfectly fine. This is also a path. C dt x1 comma y1. Sorry, this dt, right? x2 y2, and I can specify the path as a function of x as a function of y. Perfectly fine. There's nothing wrong in it. And sometimes the second one might be more easier.
I see. Thank you. Thank you so much.
Yeah. In this case, though, it might be the other way that might come out good. Okay. So we have to be judicial, especially I think on the surface of a sphere example when we do. It may not be very obvious which one to take. Here we are kind of typically we always work with y as a function of x. We might be just biased by the routine nature of it. But when once you go on the surface of a sphere, we will have the challenge of do we define the latitude as a function of longitude or longitude as a function of latitude, because we don't have any convention there, right? So we'll see that. But as of now, let me say that both are fine. Okay.
Okay. Thank you. Thank you.
At a certain extent, maybe let me keep both, right? At this point, let me keep both. So this is equal to, so if I were to do this, this would be now dt gets replaced with ds, all that remains the same. So this is x1 comma y1 x2 comma y2 to n of x ds. That's perfectly fine. And in this case, it would be the same idea. And here still, this is a path dependent quantity, right? We haven't specified the path yet, or specified means it's not very clear what the path is there. And this is again n of x ds, it's exactly the same. But now I can write this as an integral with respect to x or as an integral with respect to y. So notice dx, I think, still visible? Yes. So ds is equal to dx squared plus dy squared. So I can either write dx or dy since n is a function of x. So again, ds is equal to dx times 1 plus dy by dx squared. Or I could have pulled out the dy. So that means to say I can either integrate with respect to x or with respect to y. That kind of determines you're kind of choosing your independent variable. Right? But again, there is no such thing as this is an abstract problem. There is no such rule as to what should be the case. So two ways would be, write that down as of now. This is equal to x1 to x2, since I've chosen this to be a function of x now. So this is the x, n of x, and 1 plus dy as a function of x, derivative with respect to x, okay, squared. That's one definition. Or you can say this will be y1, y2, y, and n of x. And this is 1 plus x over the y, so x as a function of y. That's also perfectly fine. But now you immediately see the challenge here is that if I treat x as a function now, the refractive index is a function of a function, right? So this is x as a function of y. So there's an implicit dependence in there. So that's it. This is much more complicated than this one, right? Where x is a variable itself. And that was your point you were trying to mention right at the beginning, that why did I say the path was a function of x? Because refractive index is given as a function of x. So you probably came across this thought before we were discussing this.
Thank you. Thank you, yes.
Yeah. Okay, so with that feature in mind, let's not proceed here. And I should also say that sometimes it is necessary to proceed in this direction. You may not have a choice to go around. And there is a identity, probably we will get time to address this. It's called Beltrami identity. So now that we have two different ways of proceeding, you can actually say that if I do it this way, I'll get an answer. But if I do it this way, maybe it is too hard to do the problem. Not everything is solvable all the time. But if it is not solvable, then there is an identity here, right? So you say that, okay, if you do this, you get a differential equation. If you do this, you get a differential equation. So the solution of those two differential equations is the same. Right? So there is something to learn here. When you get two different paths to get the same answer, and one of them is actually not doable, then there is some information content in there that, oh, we don't know that, and we cannot actually solve for it using traditional methods, but we know the answer. Right? In that sense, there is an identity there. Okay, and we will talk about that later. So this is too early, I think. We should get a chance to. Okay, so let me proceed. So we now want to take the functional derivative of that whole expression. So the idea is we want to minimize this. So minimization is take the functional derivative and then set it to 0. So functional derivative of t, let's say c times t, right, with respect to y as a function of x would be c times t y plus delta y minus c of t y and divided by delta y. Let me say delta y of x. And in the limit, we have set the limit delta y tends to 0. This is delta y of x tends to 0, but there is a delta function we identify in those scenarios. Okay, so what is c of t y plus delta y? So this is c of t y plus delta y. That's equal to down here. So that's x1 to x2 dx. I'm only changing y. I don't have to change x. So n of x remains all intact, right? That's again the advantage. If you had to flip it, then you have to change the refractive index as a function of x, which is nothing wrong, but it's just that it's more work. And there's 1 plus e by dx of y plus delta y. Maybe I should be careful here. Since I've already used, I'm going to take the differentiation with respect to x, I should keep this x prime. Right, so this is y of x prime plus delta y of x prime. And this whole thing squared. That's your change and delta y. Let me write this one more step to this. 1 plus. If I were to square this, let me write this y plus. And our idea would be that this change is going to be small, so we can actually make an approximation in there. So the second order, I'm going to right away drop out this n of x prime, writing more steps this way. That's 2 times dy by dx prime and d by dx prime. Is that clear? I've not written the dependence. Write the dependence. Plus higher orders, plus there is a second order term there. Is that clear? Any confusion there?
No.
Okay, so, and I'm just dropping this because it's higher order. It's only the leading order that will contribute. Okay, so I still want this is inside a square root, not very convenient. So let me do some more tricks to this before I start subtracting things. I take this common out. This is equal to x1 to x2 x prime and x prime. Take this 1 plus dy by dx prime squared. So I'm taking this whole thing out because that was my original stuff, right? So what is left afterwards is, if you want, as a, so I'm going to raise this to half. So it's 1 plus 2 times. And I'm not going to use a notation where derivative with respect to the dy by dx is equal to y prime. This shouldn't be confused with, there is a derivative with x prime also, right? So we will write this as x prime. So the derivative is with respect to x prime, but the derivative itself is with respect to, how do you say it? So that's a notation. So this is y. Or how about that? I won't even write the x prime. So it's understood, I guess, that whatever is there inside is x prime. So I think whenever needed, I'll bring it up. Is that necessary? Or maybe not. Hold on. Too early. So this is dy by dx prime times d by dx prime of delta y divided by the whole thing in the denominator, right? 1 plus and no square root. And this is plus or more higher order terms raised to square root of 2. Okay. Hopefully I didn't confuse that too much. Okay. One more step. Putting in details here. So this is x1 to x2, dx prime n of x prime 1 plus dy by dx prime squared. It's a small quantity, 1 plus a very small quantity square root. So you remember your expansion. 1 plus any small quantity, alpha, let's say raised to half. If alpha is very small, this is the same as 1 plus 1 by 2 times alpha plus higher order terms. So the power of the, this is binomial expansion, right? So whatever is, you raise it to times alpha. So this leads to 1 plus 1 by 2 times 2 cancels out. 2 cancels, so this is d by dx prime and d by dx prime. And I put just this x prime there because that's going to play an important role in a few steps. Okay. Hopefully, until there, it should be very clear. Any questions?
No, thank you.
Hey, Sammy, I think that's one of my friend who is attending there. I noticed that. Sammy, is that you there?
Hey, Tejas, yes, it's me.
Hey, yeah.
Hi,
So
everyone.
Ken, that's one of my friends. Friend, he was just saying he wanted to see what's going on. So he works in Caterpillar in Peoria. So a good person to be in touch with.
Nice to meet you.
Yeah, hi, Kenneth. Nice meeting you. Hi, Tejas. Hi, everyone. Good morning. Sorry to interrupt your lecture suddenly without.
We are only at least one person attending in live, and hopefully Harsha attends to it later on. So yeah, so not much interruption, I'm sure. Yeah. Okay. So Sammy, this is we are talking about the Fermat's principle. Just to quickly go over it. So we have a medium which is in the x direction. This is layered medium, or layered or continuously refractive index is changing in the x direction, but not in the y direction. And how is it changing? It is 1 as far as you're less than a, so it's vacuum, and then it grows in time. Grows in position. As you get deeper and deeper into x, the refractive index goes higher and higher. That means speed of light becomes slower and slower. And the idea is that if you want to go from one point to the other point, what's the shortest path possible? So we construct this integral, and we are trying to do functional derivative. But the problem is just that. Okay. Okay, Ken, any questions at this stage until here?
No, thank you.
Okay. So now when I subtract these two quantities, C. So I made a change in Y. Right, so that's my change. So since everything is not visible on the board, so this is Y plus delta Y. Right, that's the change. And I have to subtract out the original time if you want, or time times C. Right, C is just a unit there. And the original is without the square brackets, right? That's how much time it takes to go from point x1 to x2, in principle x1, y1 to x2, y2. But since you're treating it as a function, you can subtract that out. If you subtract that out, this is the change in time for any arbitrary path, and we would like to minimize that. So this is a change between two paths is just this multiplied by this. So it's x1, x2, x prime, x prime, right? So that's here. Now this piece is exactly the same, similar to the one we have in the denominator. So there's a cancellation in there. So let me write it in the following manner. So this is dy by dx prime divided by 1 plus dy by dx prime. If you want it very much in detail, so this is x prime dependent, that's x prime dependent, and that's squared as a square root. All this is normal functions, nothing new in here. And what we have is that there is a derivative. Like if we were doing simple derivative in the first principle way, this would just be a variable there, right? This will be the small change in the derivative or the variable. But here it's a function. This is a function, a change in the function. And that's where the whole difference is going to be, but that's the only place where the difference is going to be, and that will make our life very easy. So our functional derivative, so this is the important piece. This is all algebra at this stage. Change the functional if you want due to a change in the function. So that's the change in the functional. But I have to take a derivative now. I divide it out, right? So we are doing y plus delta y minus c divided by, this is delta y of x, right? This is with respect to x. Notice everything here is an x prime dependent. That's because it's a dummy variable inside the integral, right? How the variable with which you integrate should not matter at all. And you're taking, of course, the limit delta y tends to 0. So let me write that also. It's limit delta y tends to 0. That's a quantity we are interested in. Notice this is y of x. That was our main point. That this doesn't see the integral at all. Right? This is a function of x. That's an integral over x prime. It goes through. In fact, it doesn't see any of this. It can go through in and out of wherever it wants to. And we will like to keep it all the way with respect to this. So this is equal to x1 to x2. Hopefully this is visible. Yeah. Okay, x1 to x2 goes through. This is dx prime of x prime, and this is derivative, just functions of x prime, just copying from the top. All that is fine. The x dependence also goes through this derivative, and that's where we want to keep it. This is x prime. And here, let me write it in square bracket, but nothing special about the square bracket. These square brackets, remember, mean that these are functionals. This is just a, because I'm out of brackets. So here I write limit delta y of x times delta y of x prime over delta y of x. And that we recognize in our definition of functional derivative. We try to motivate that these are variations at x with respect to x prime, right? So if I were to show this here, so we have a arbitrary function y of x, and then I can make a small change here. Right? So this is delta y at x, and there is another change here. That's delta y of x prime. At each point x, I can make a small change delta y, and we are saying that these are independent variations. Like one could say that, oh, if I make this a small, that is a continuous change on the other side. So that's one way of making a variation where the whole function is like acting as a single piece, and you disturb one side and everything else gets disturbed. No, that's not what we're doing. Here it's completely independent. We're saying the change here is completely independent of the change here. That means that these two are independent, and that will, using that feature, we recognize that this is delta function. Why delta function? Why not a Kronecker delta? Because these are infinite of them, and they should all add up to 1, and we tried to motivate that earlier. So this is a delta function, and let's proceed with that feature. Any questions at this point? Ken?
No, thank you.
Sammy, it's normally connecting, you came in late, so
Yeah, I think I can. I'm following. Okay, so far.
probably. Okay, so let me rewrite this. So what we are saying is that the change in function with respect to y, and that is a c also, that's a c. With respect to y of x is equal to x1, x2, x prime, and of x prime, and what should I do? Yeah, let me just write this explicitly. This is x prime. And what we have used is, this is nothing but delta function. So that's like we put in all the concept in this part. So what's the big concept here is that we are saying delta y with respect to x prime over delta y with respect to x. In the limit, delta y tends to 0 is actually a delta function. And we pretty much said, if we were to think of vector calculus, this is kind of a completeness relation, right? In vector calculus, you see this as times r is equal to 1. Or, in another way, d by dxi of xj. Like derivative of x with respect to y, they are independent, that's 0. Derivative of x with respect to x, that's 1. So that's delta ij. If it is discrete, that's kind of simple, but this is continuous. So instead of this being 1 or 0, right, at one point it's go to infinity because overall it has to add up to 1. Okay, so that's good. But now we can use the definition of delta function, right? It's just remember your delta function dx prime f of x prime delta of x prime is equal to f of 0. Well, wherever this argument goes to 0, like as far as it is within the limits. But if it is a derivative of this, derivative of a delta function, then you take the derivative of the function and then set it to 0 with a negative sign in there because you integrate by parts, and you can then use the top identity. The negative sign comes because of the integration by parts, and then you evaluate it at x equal to 0. If it is x minus x prime, then you will evaluate it at x. So our functional derivative pretty much becomes almost an identity at this stage. This is equal to, this is what will lead to later on what we'll call Euler-Lagrange equation. So we have to take the derivative of this whole piece, everything that's in front of the derivative of the delta function, and that's all that is, and we replace x with x prime. So take the derivative with respect to x, the negative sign, because this is negative sign, and this is dy by dx now. All that was x prime gets replaced with x, divided by 1 plus y function of x respect to x. And one more thing, right? There's a refractive index. So refractive index. That's it. So that's your functional derivative of that whole piece. Any questions at this stage?
No, thank you.
Okay, so that's taking the functional derivative, and then comes Fermat's principle itself. Now, Fermat said that this change has to be zero, right? If you want to minimize anything in normal calculus, if it's a single variable calculus, you would say the slope is zero, right? So let's say minimum. So wherever the slope is zero, that's what is the extrema condition, I should say, not minimum. The local minima or maxima is zero. And Fermat said that whenever light is going through a medium, it actually tries to minimize the time it takes, and the time it takes to go from x1, y1 to x2, y2 is exactly this amount. So in this case, it is a continuous variable. So there are lots of variables. This is not one variable, infinite variable system. In principle, that's what the idea of a functional is, but we just have to set that to zero, right? So setting it to zero means that is a differential equation. So Fermat's principle says, so Fermat's principle now. So that's where the physics comes. From this point on, we are just analyzing the system, but like, remember that this was just an example. We're not doing Fermat's theorem too much in detail. There's a whole array of optics you can develop from here, and this is called an iconal. You can write on Hamilton's Hamilton-Jacobi equation for this. So there's a whole field of that one can work out starting from here. But we are just doing one simple example. So Fermat's principle says that this is zero. In fact, I don't have to write. Of course, Fermat did not write it using functional derivative. He just said that the variation with respect to time is equal to zero. So that was an interpretation. If this is zero, we have a differential equation. So that's equal to zero. So this is d by dx of the refractive index n of x dy by dx. Everything is now as a function of x divided by 1 plus dy by dx square is equal to 0. If the derivative of something is as 0, that means it must be independent of that variable, right? So it is not dependent on x, and we get a differential equation basically. And remember, the differential equation also requires initial conditions, correct? So these are the initial conditions we will what to invoke now. So this is equal to 0 means that n of x times dy by dx, and explicitly writing this derivative, you can write like prime if you want. There's nothing wrong with that. 1 plus dy by dx squared is equal to a constant. Let me call that constant C1. Should I call it C1? Yeah. What did I call it? Let me, so that I can match with my answers. Let's see if I called it anything about. Yes, I called it N0 for some reason. Not a good notation, I suppose. because it is n times something. Let me call it C. Let me not use my notes. So this is C. So let me call it C. C1. I used n0, but that's not n0, right? N0 times this at some value, right? We have to choose that C. Okay, whatever. So let's square this quantity. We want a differential equation, right? So let's collect all the derivatives at one place if we can. So square this. So n squared, n of as a function of x squared. Then we have dy by dx squared, and that's equal to c1 squared, and multiplied with 1, and then there is plus c1 squared dy by dx. Remember, c1 is a constant. This does not depend on x. This is a constant with respect to x. So what is the derivative dy? So get this all on one side, right? So n of x minus c1 squared, and then take it out. So this whole thing can be simplified as derivative of y with respect to x is equal to c1 divided by n of x squared minus c1 squared, and then there's a square root. There is a plus or a minus there in principle, but c1 is arbitrary, right? So I'll absorb that plus or minus inside c1. I did not specify c1 yet, so c1 can be specified. Can absorb that plus or minus. And then, okay, so that's your differential equation there. But we would like to find the path, right, for our given system. What exactly is the path? So you would like to solve for this y of x, right? Whenever this is equal to 0, that's a minimal. That path takes a minimum, and provided we know C1, that means to say that at some point you would like to know this function if you want, and we'll try to figure that out for any specific scenario just to get a feel for what C1 is. But after that, we would still like to solve this differential equation that involves integrating this. So let's go ahead and integrate it, and then we'll come back and look at what C1, and there will be one more constant when we integrate again, right? What that means actually. Any questions at this stage?
No, thank you.
Okay, so that's dy by dx. So, oh, but I have to put my variable in there, right? Because yeah, I have to now, if I have to proceed from this point, I have to specify my n of x, right? So, yeah, so now I need to specify my problem. Right, so let's see. So let me rewrite that. dy by dx is equal to c1 over n of x squared minus c1 squared. Right, that's fine. Oh, and remember, n of x was equal to 1 if x was less than a, and this is your x over a if x was greater than a. That's our problem. And now let's see what is so let's I can put this in there. Right? So this is x square minus a square if you want. Can I learn something about C1 here? Let's see. If x was equal to 0, right? Maybe then there is a minus C1 squared. We don't even know whether C1 is positive, negative. We don't know that yet. Is there anything else you can learn about it? I don't know. Okay. Any thoughts on what C1 is at this stage? Let me see my notes. Yeah, nothing as such. Yeah, but let's leave it alone as of now. Okay. Let's proceed and solve this, correct? So we have to integrate. So let's just do this as a as an integral problem, right? So integrated with respect to x. So we get y. So this is integral of dy is equal to integral of dx c1 over x squared over a squared minus c1 squared. Right, and there will be a constant afterwards, right? Plus a constant, this will be c2 whenever we integrate this out. That c2, I can absorb it into y, so that will be y minus, let's just say, let me do that. So this is y is equal to, how do I integrate this out? X squared minus something. What is this? So we have this cosine hyperbolic square of theta minus sine hyperbolic square of theta is equal to 1. That means to say that cosine hyperbolic square theta minus 1 will be equal to sine hyperbolic square theta. So that seems to suggest that if I might be able to substitute x with cosine hyperbolic theta. So let me substitute, let me pull out a c first of all. That cancels out. So it is x over a times c1 is equal to cosine hyperbolic theta. So that's a substitution I make. And dx then is equal to x over a times c1 is equal to sine hyperbolic theta times dt. Right. So integral, not a definite because this constant c2 will take care of the definiteness there. This is equal to sine hyperbolic theta over times d theta times a over c1 there. And c1, when I pull out the c1 that's gone, whatever is remaining is sine hyperbolic theta. Sorry, cosine hyperbolic square theta minus, which is nothing but sine hyperbolic theta. So these two cancel out. And then there's plus c2. So sort of becomes very simple. This is equal to theta over a times a over c1 plus c2. But theta was sine hyperbolic inverse of a over c1, correct? So this is equal to, y is equal to, still in the board space? Yes. So y is equal to 1 over a c1 times theta, which is cosine hyperbolic inverse of x over a c1. Right? And plus c2 of this. Okay, so what is that function? Is that a familiar function by any chance? Y as a function of x, which is cosine inverse of a cosine hyperbolic function. Ken?
I'm unfamiliar with it, to be honest.
This is what is it? I should actually first invert it. Correct. Did I do this correct, by the way? AC1, I did d theta is dx. Yeah, everything is correct, right? At this stage, dimensionally. C1 had the dimensions of, C1 is dimensionless apparently. And A has the dimension of, what was A? What was A? Where did A show up from? Up here. Oh, A was the distance. So, yeah, that is some problem here, right? What happened to the A should be somewhere in the numerator.
Yeah, I think your substitution might be, I don't know. It just looks like when you replace the dx, it should be sine h times AC1, unless you went ahead.
Oh yes, AC1 times that. Yeah, that's good. So because this should be AC1 in the numerator, right? Yeah, I like that. AC1 in the numerator. Thank you. Yeah, thank you. So this is AC1 in the numerator. Okay. Otherwise, dimension will be the problem. Okay, that helps me a lot. So this is A times C1. Great. Okay. So I can invert this actually, that's what I was looking for. Then dimensionally was done. And oops. Okay, so I divide this out. So let's do this in two steps. A times C1 minus C2 over A times C2. C2 has the dimension of distance times C1. That's equal to, let me write that in one step. Okay, great. And that's what probably, that might be, maybe I should have asked the question now as to is that a familiar function or not. So this is x as a function of y, and this is called a catenary. Maybe you've heard the name. It is a catenary if I have the C2 equal to 0, but this is just a shifted catenary if you want. And where do you see such a function? The classic example is, we are very close to St. Louis. We can say the shape of St. Louis arch, right, is a catenary. Okay, maybe an inverted catenary. A better example is when you have a rope hanging about 2 points, like a power line under gravity, which we will again show probably in an example in class or in a homework. This curve is actually part of a catenary. And so that's also a cosine hyperbolic function. It's interesting because it is consisting of dimensionless quantities. So you can, there is no scale in the problem, if you know what I'm talking about. Like you can always squeeze this function as much as you want and fit it into anything. So there is no scale in the problem. Okay, all that is good, but now to put this all together in our problem where refractive index was given, we should have some C1 and C2s there, right? Remember what we are saying is that we have to go from one point to the other place using, so this was our feature, right? So this was Y, so that's your X, and somewhere here is A, and beyond on the left side is vacuum. So now let me specify some conditions, and let me see if I have a particular case. Yeah, Y of X and yeah, so let's say that it starts from this point, right on the boundary. Like we know that somehow light has reached that already. And right at that point, it is actually going vertically. So that's a very extreme example. Right? Light would preferably come at an angle, right? That's just to simplify things. So light is actually going, in a sense, vertical direction, but very slightly, having a very slight, tiny slope to the right. So it is actually going this way, but we are going the extreme situation where you're actually almost vertical. That's just to get the solution very clear. So what's our equation? So y1, let's say, is equal to 0. So x1 is equal to a, y1, that is position y as a function of x, that's equal to 0. That means it is right here. And let's also say the derivative of y with respect to x at x equal to x1. That's your derivative. That's going to infinity. So that's our conditions, if you want. Let's go back and see what is C1 and C2 now. Let's look for C1 first, hopefully that's better. So let me go back and remember your equation with the derivative, that dy by dx is equal to C1 over n of x 0 minus c1 squared. Hopefully this comes out a nice feature here. So at, oh remember this is x squared over this. So at x1, at x equal to a, this is equal to 1. And at the same point, this is equal to infinity. So we are saying this is approaching infinity, very large. Right? That's equal to c1 over 1 minus c1 squared. Can we say something about c1 then? If c1 over 1 minus c1 square is large, then c1 has to be okay. C1 has to be approaching 1, correct? Is that correct? Is that correct? Oh, you guys cannot see. Sorry. I was saying that, sorry.
Oh, I see. Yeah.
Like I was saying, I wrote this equation down, and then I want to put this initial conditions in here to gather the conditions here. So right side is infinity because I said this is, I hope you guys could see when I was doing this. I think you could see it until here, right? So I'm saying this is derivative is infinity because slope is pretty much vertical. So that's infinity, c1 over x is equal to a, so that's 1 minus c1 squared. What can c1 be? Probably not 0, right? No, it's not 0. Huh. Let me see. I'm stuck here a little bit. Hold on, let me think a little. Let me try to look into my notes. Help, Sammy? Evaluate the total time.
Yeah, I'm with you, Shajas.
Yeah, I was asking for help. Okay, so
Okay, let me. What's the question?
No, I was just wondering. This doesn't imply that C1 is equal to 0, correct? That's not correct. Okay, let's leave that alone. And
Yeah, that implies I think C1 equal to 1, right?
Oh yeah, that's what I was trying. Yeah, I did say that, right? But then I got distracted. Yeah, this implies C1 is equal to 1. Yeah, perfect. Okay, thank you. Yeah. Oh, yeah, I think that's what I said earlier, but then I got again distracted because I was thinking C1 is equal to 0. But no, C1 equal to 0 is fine. Yeah, no, this is good. Yeah. Okay, nice. Right? So C1 is equal to 0. So, sorry, C1 is equal to 1. So this all goes away, right? So we have immediately that cosine hyperbolic of y over a minus of c2 over a is equal to x over a. So that's one condition gone there. And now, what else do you want to say? What about C2? Is there, can we gather something about C2? We also require, yeah, we have only used the condition, the second condition, right? We also want y to be equal to 0 when x is equal to a, right? So let's put this condition again here. So this is cosine hyperbolic of y is equal to 0 minus c2 over a is equal to when x is equal to a, this is equal to 1. Cosine hyperbolic of what is equal to 1, it comes out to be c2 equal to 0. So this implies that c2 is equal to 0. Okay, better. So a lot of simplification, and what we get is x is equal to cosine, or better, x over a, right? So x over a is equal to cosine hyperbolic of y over a. Since we are interested in y as a function of x, it doesn't matter actually. It's nice to see x as a function y cosine hyperbolic of y. So what will this function look like? So this is your y. Remember, our problem is refractive index increases from a point x equal to a. So that's your a. And if light were to slightly make a very small delta tangent with respect to the vertical, this will actually go like this. That's a path of light, and this function is, if you think of it as x as a function of y, this is cosine hyperbolic of y over a, x over a. If you think of it, this is the other piece of the cosine hyperbolic y function. Yeah, it's interesting to ask, once we have this path, this is the path that takes the minimal or gives you the minimal time, right? How much time does it take actually to go from one point to the other point? Okay. And that's good. We can substitute it back. But especially if you go all the way to infinity, in this case, it may not be counterintuitive because you're traveling an infinite distance. It might come out in finite time. But sometimes what happens is, which is very common in these kind of problems, is that when you actually calculate the time for these things, it comes out to be infinity. And we did come across such an example, and that was the pendulum, right? If you were to solve the pendulum exactly, without small angle approximation. So we call your pendulum problem. So if you have a pendulum and we don't make a small angle approximation, and if you were to oscillate and then release it from a very large angle, this is pi naught, let's say, release it from a very large angle, in fact, take it all the way to pi, right? Almost pi. If you keep it pi, then it is actually not, it will never fall, right? Even though it is unstable. But with a very infinitely tiny element, if you were to actually drop it and then ask how much time does it take, it will take infinite time to reach the other side, right? Very counterintuitive. Similarly, in your homework, remember this whole problem is inverted, as I said. Here x increases to the right. In your homework problem, x is actually 1, instead of x increasing, this is 1 over x. N of x is a over x. That means to say that as x goes to 0, the refractive index gets higher and higher. So if light was coming from the right, from my right side to the left, then it starts getting slower and slower as it approaches this x is equal to 0. And there the question comes out interesting is that what is actually the time taken to go from x equal to a to x equal to 0, and be prepared for an infinite answer. So let me, since we have a few minutes, let me say something about the homework problem more specifically. Any questions here until now, as of now?
I have a quick question regarding the integral for the hyperbolic functions. I just I didn't see that it was obvious that the sine h over the square root of the cosh squared minus 1. I didn't see how that would equal that cosh negative 1.
Oh, okay. So let's see.
Like the cancel that you did. If it's just math that I can look up later, I can do that.
Okay. So this is the one you're talking about, right?
Yes.
How did I cancel this? Notice this identity.
Oh, so it's trivial. Okay, yeah.
Right.
I can see that.
So,
yeah.
So because cosine hyperbolic theta minus sine hyperbolic theta squared is equal to 1.
I see.
It's like trigonometry, but except that there's a minus 1 there.
Right. Thank you. Thank you. I didn't see that.
Then that cancellation is immediate, and from that point on, it's kind of trivial.
Yes. Thank you. Sorry. Thank you.
Yeah. No. Important. Yeah. Any other comments or anything?
No, thank you.
Like otherwise, the solution was clear. Right? Once that mathematical function is there, that comes out. Okay, here is the interesting part in your homework. So in your homework, what you do is, again, we have y, correct? And we have x. This is the actual space, and there is z also, but there is nothing happening in the z direction. Everything is happening in a plane. And there is a line x equal to a here. And now what happens is that now I say that refractive index is equal to 1. So this is vacuum on the right side. So this is 1 if x is greater than a. What happens if x is less than a? I say it is a over x. Right? So right when x is equal to a, it is almost vacuum, but then it starts increasing as you go deeper towards x equal to a. It becomes denser and denser to the extent that it blows up at x equal to 0. Very. So this is kind of what is happening. So that's 1. That's a. And this is 1 over x, a over x, so more specific. So it's clear that if light tries to come in this direction, eventually it's going to get so dense that it is almost going to stop. And we've also wanted an initial condition there. So there I say the initial condition can be that it comes almost tangentially, but to the left, right? So it is sort of going in this direction. But make the slope smaller and smaller so that it's almost vertical in this direction. Oh, again, I kind of cut out on the y direction. Okay, sorry about that. Hopefully, you didn't. I think you didn't miss too much there. Okay, now the interesting part is that there it was a catenary. Here, it will come out to be a circle. The path that you will get will be a circle. That's very interesting in the sense you can always ask, does a light ever go in circles? Yes, it does go in a circle, and that's an example. Right? So send light in you construct such a medium and make the light go almost tangentially, and it will go in a circle. And then one would think that, oh, that's nice, so I can go light in a circle. So why not make a medium exactly symmetric so that it starts going this way, and again make it symmetric in this way, and that goes this way, and make it a complete circle and make it go in circle. But that doesn't happen because you realize that if you were to calculate the time it takes, theoretically, yes, it can go, but the time it takes to go 1/4 of that is already infinity. So it will never cross the first quadrant, so forget about it. So in that sense, it's not completely physical or realizable. But nevertheless, very nice example where light actually exactly takes a circular path. So that's your homework. So instead of this catenary problem there, you will get a trigonometric, real trigonometric function, and that integral will be doable, and you get a equation of a circle. I think that's what happens, but yeah, do it. And we'll come across that. Okay, helps? Any questions, comments? Hopefully useful.
Yes, very useful. Thank you so much.
Okay, so let me stop. Yes, sorry, I got a little caught up in that constant I was trying to derive. Yeah, I lost that a little, but good. Oh, Sammy left, I guess. Yeah. Okay.
Yeah, he just left. So
okay, good. Okay, yeah. So shall we stop here? Anything you have in mind, Ken? You want to ask?
No. I think I'm understanding this homework pretty well. And one thing I do want to ask is you said C1 for the constant instead of n and not, and I was just curious why. You said you mentioned something about like a multiplication or something.
No, yeah. Y means okay. Means first of all, a constant. That's what I call. Okay, that's one answer. Straightforward answer is that who cares what I call? Correct.
Right.
But earlier, what I said, okay, this is where it shows up, right? So we have n of x times derivative of dx over 1 plus dy by dx squared, right? That's a constant. I want to call it something, right? It would be nice if this was not there, then it's nice to call it a refractive index. Like when I use n naught, the understanding is that somewhere at some point in x, this is exactly equal to n naught. And at some value is equal, but it's not because there is this derivative multiplying, right? You see what I'm saying?
Yeah, I think so. That it will be equal to some n, right? If there wasn't a derivative.
Exactly. Instead, this is this, right? Some value where 0 means at some x, right?
Mm-hmm.
So why call it n naught when it is not, even though this doesn't have a dimension, it is okay.
Oh.
But it's kind of misleading to call it n naught because it is multiplied by something else. So call it some other, why use n at all? But
I see.
It's a constant. I can call anything I want as far as it is clarified that it is not that. Right? But I think first time when I was doing this, I just called it n naught, and when I was looking at it now, I did not call it. But nothing wrong in calling it n naught. It's just probably a little misleading. Typically, when you write n with a subscript 0, it seems to suggest that it has some connection with n.
I see.
Did I clarify?
Yes. Where I mean, like, technically speaking, that whole thing would be equal to C1, right?
Exactly.
Yeah. No, that makes a lot more sense. And I get it's just a constant. I was just trying to like stick with, the norms, and yeah, that makes sense. Okay.
Okay, good. Anything else you could think of?
No. I think I'm understanding this very well. So thank you so much.
Good. Okay, Ken. So I will stop here then.
All right, sounds good.
Yeah, stay warm. Are you coming to the department? Do you have to teach or anything?
No, not today. They went ahead and canceled labs this week. I guess for students that are living further away,
That helps.
Yeah, so they're gonna do a combined lab for next week.
I see. That's I think that's a good call, because there's always at least few students who are really far away, and it's not really cleaned up everywhere. Only the main roads they have done a good job, but remote places it's always hard.
And I just feel like people wouldn't show up if they tried to have labs, right? So, but yeah, I decided to not risk it because over where I am, it's still pretty. It's like over 7 inches, 8 inches of snow still. So.
No, it's a good call. I think it's a good call. Yeah.
But I will be there Tuesday, hopefully. Right.
Yeah. So. Hopefully all this weather will get normal by this weekend. Yeah. Okay, good. I'll stop here, Ken. Okay.
All right. Sounds good. You have a good rest of your day and weekend.
Sure. You too. Thanks. Bye.
Okay. Goodbye.